Hey everyone, to start off today, we're going to review yesterday's concept. So we're going to talk about isotopes very briefly. The catalyst question for today, which you'll find on the previous slides, is using ptable.com, determine the number of neutrons in the following atoms. All right, so this you'll see here is our isotope notation. And to the right, I've written the atomic number or the number of protons for each of these atoms. So the first element is phosphorus. I just go to the periodic table, see that top number, and I see that it's 15. In order to get the right answer for this, what I'm going to do is I'm going to take the atomic mass, or the total number of protons plus neutrons, which it gives me as 34, and I'll subtract from it the atomic number, which is 15. Okay? And so for the rest of these, we just follow that simple step. Carbon is 14, and then I'm going to subtract the atomic number, which I've written as 6. Lithium has an atomic mass of 9, so I'll do 9 minus the atomic number, which is 3. And I'll go to the answer on the next slide here for y'all. But this is just the overall process for solving these types of problems. I take the atomic mass, which is this number that it gives me within the isotope notation, and I subtract the atomic number. That gives me number of neutrons. Last one, sulfur, 33. So it has an atomic mass of 33, atomic number of 16. Okay, so this is what your work should look like for all of these problems. And if I go to the next slide, you'll see the answers. So it would be 34 minus 15 to get 19 for this one. 14 minus 6 is 8. 9 minus 3, you'll see 6. 238 minus 92 gives us 146. And 33 minus 16 is 17. All right, so these are our correct answers. This is how you get to the number of neutrons if you're given an isotope symbol. And then you can, of course, look up the atomic number or number of protons on the periodic table. I'm recording the video right now. This is very meta, inception. All right, our I can statement today is I can define the different types of nuclear decay and predict the products after a decay event. So a lot of new words here we'll go over. The first one is nuclear decay. So when you hear nuclear decay, think of radioactive decay. So you all kind of know what radioactivity roughly is. It's not very good, but when you hear radioactive, you think of things like Chernobyl, Geiger counters, the little people in the full-on COVID suits pointing their little guns to see if there's any radioactivity nearby. Well, what radioactivity is it's a result of an unstable nucleus or unstable nuclei. And remember, in the nucleus of an atom, think for yourself, what do we have? In the nucleus, we have protons and neutrons. So if an atom is going to be radioactive, it has a nucleus that is unstable. All right, well, in an attempt to stabilize the nucleus of this atom, the atom will undergo what's called a decay. And when you hear decay, I want you to think decomposition. Okay, so when you hear decay, think decomposition. That'll make sense in just a second. We have 3 main types of nuclear decay. Those are alpha decay, beta decay, and gamma decay. So you could also hear these as alpha radiation, beta radiation, or gamma radiation. Looks like my screen's messed up. Okay, problem solved. Now, in order for us to show what kind of decay happens, we've got to have a new terminology. It's not really new, it's just adding one little wrinkle. So if you take a look at this right here, the way that I'll be showing atoms is using the isotope symbol, where X is the element symbol, A is the atomic mass as we've known it, and we're gonna add Z, the atomic number. So for an example, I'll do carbon, and I'll do C14, the example from the bell ringer, from the catalyst. So the way that I'd show this atomic symbol, this nuclear symbol, is C. I'll put the atomic mass in the top left corner, which is 14. That's this number right here. And then I'm going to put the atomic number, or the number of protons, which is 6 for carbon. Get that from the periodic table. The other example that we had from earlier, lithium, 9, and it's got a 3 down here because that's the number of protons. So Z, number of protons. So now we're going to go over the examples of each different type of nuclear decay. Remember, when you hear decay, think decomposition. So the first type of decay is alpha decay. Alpha decay occurs when the atom breaks apart and emits a helium nucleus. And a helium nucleus is 2 protons and 2 neutrons. So let's say I've got this atom, Bi-209. This is an isotope of bismuth, Bi-209. It's got 209 protons and neutrons in the nucleus, and it's got 83 protons. That's not what I wanted. So it's got 209 protons plus neutrons. That's its atomic mass. And it's got 83 protons. That's its atomic number. We get that from down here. Now, in an alpha decay, what I said was decomposition happens. So in a decomposition, remember, I start with one thing that then breaks apart to form multiple others. In an alpha decay, what happens is my atom breaks apart to form a helium nucleus, and then whatever's left over after that helium nucleus leaves. So the general equation for an alpha decay is this equation up in the top right corner. So I've got X, which is my element symbol. I've got the atomic, my dog trying to sit on my laptop. I've got the element symbol, which is X, A, which is the atomic mass, and the atomic mass is going to go down by 4 because that is the atomic mass of a helium nucleus. And then it's going to be the atomic number, or Z, minus 2, and that's because that is the atomic number of your helium nucleus. So notice, I started at bismuth 209 with 83 protons. After the decay, I go from 209 to 205 as my atomic number, or as my atomic mass. And then from 83 to, that's a typo, 83, good thing I got this little pen here. 83 should go to 81. So 209 minus 4 gives us 205. That's where that number comes from. And then 83 minus 2 gives us 81. So this is your alpha decay. I know something is an alpha decay when my products are, 1, a helium nucleus with an atomic mass of 4, atomic number of 2, and then another new atom that matches up with whatever I've lost from the previous atom. So in a beta decay, maybe it switches. Yeah, in a beta decay, I'm not emitting a whole nucleus. It's not going to be a helium nucleus. It's actually just an electron. And it's a high energy electron. And my general equation for a beta decay is the element symbol, the atomic mass is not going to change, and the atomic number actually goes up by 1. So if I'm looking at an atom of astatine 210, At210, its atomic mass is 210, its atomic number is 85. It goes through this decay, and remember, when you hear decay, think decomposition, starting at 1, breaking apart into 2 separate things. One of my products is going to be an electron, and this is how an electron is shown. Remember, electrons have no relative mass, they're very small, and they have a charge of -1, so that's where this -1 comes from. Remember, protons are positive, electrons are negative. Now, if I take a look at the products of this, my A has not changed, but my Z has gone up by 1. Now let's take a look at why this might have happened. If I look at this like a math equation, I want it to balance out. If I look at this like a chemical reaction, I want it to balance out. The numbers on top, so my A on the left is 210, and all the numbers on the top on the right have to add up to 210. So I've got 210 plus 0. And 210 plus 0, of course, adds up to 210. On the bottom, the same thing has to be true. The bottom number on the left has to equal the bottom numbers on the right. So I've got 85 on the left, and then I've got 86 plus -1. Well, 86 plus -1 is the same thing as 86 minus 1, which is 85. So this checks out. This is the correct equation for a beta decay. Let's actually go back to alpha decay and see if this is true. So again, the numbers on the top on the left side of the equation have to equal numbers on top on the right side of the equation. So I've got 209 on top on the left side, and then I have 205 plus 4 on the right side. 205 plus 4 is 209. So that adds up. On the bottom, 83 on the left. 83, my atomic number on the left. So on the right, it has to add up to 83. I've got 81 with my lovely typo and 2. 81 plus 2 is 83. So that checks out. So this is a chemical equation, just like we learned how to do the balancing and do the conservation of mass. The same thing still applies here. Got to have the same number of protons and neutrons on both sides of the equation. Finally, gamma decay. In a gamma decay, the atom emits a super high relevance, super high energy radiation. So you've probably heard of gamma radiation. If you like superheroes, the Hulk supposedly got Hulkish because he was exposed to a lot of gamma radiation. Now, it's not exactly how it works, but it's a clever idea. It is super high energy radiation, and that means it is not mass. So if we take a look at this equation right here, what happens is I start with an atom. In this case, I'm starting with americium-244. So it's got an atomic mass of 244, an atomic number of 95. This is going to decay. It's going to break down. But on the right side, I'll still have the same atom with the same atomic mass, the same atomic number, but it's emitting this radiation called gamma radiation. And this symbol is gamma. It's a Greek G. And you just know when you see that, it's a gamma decay. It's releasing a very high amount of energy. So I think, yeah, so let's do some practice problems. So it says an atom of Pb208, lead-208, undergoes an alpha decay event. Predict the products. So first thing I've got to do is I've got to write my element symbol, which is Pb, that's lead. Reminder that the overall atomic symbol for nuclear decay is going to have to look like this. So I've got my element symbol here, atomic mass in the top left, and atomic number in the bottom left. It gives me my atomic mass, which is 208. I'll write that here. And then my atomic number of lead is 20. Oops, reading the wrong thing. My atomic number of lead is 82. So 82 goes here in the bottom left. Now, in an alpha decay, what is the one product we know we're going to have? So go back through your notes and see what is the one product I know I'm going to have after an alpha decay. You are right. Thank you for going back to check your notes. We're going to get a helium nucleus. Well, what does a helium nucleus look like? Well, it's got the element symbol He. It has an atomic mass of 4, an atomic number of 2. So I know one of my products of this reaction is going to be 4,2 helium. Okay? Let's figure out what my other product is going to be. So I've got to make my numbers on the left add up to my numbers on the right. Another way of thinking about this is my atomic mass on the left side is going to lose 4. So I'm just going to subtract 4. So 208 minus 4 is 204. And then the same thing applies for my atomic number, Z. Start with 82. I'm going to have to lose 2, which means it's going to be 80. The next step is to look at the periodic table, find an element with an atomic number of 80, and you'll see that this is Hg, or mercury. So the two products that we'll get from an alpha decay are a helium nucleus and mercury 204, Hg 204, atomic number 80. Next practice problem. An atom of P32, phosphorus 32, undergoes a beta decay event. So first, pause the video, try to do this on your own. And when you're done, press play. So the first thing I've got to do is draw my symbols. Phosphorus is my element symbol, it's P. It's got an atomic mass of 32. If I go to the periodic table, I can see that the atomic number of phosphorus is 15. Now we've got to remember what is the number one have-to-have product from a beta decay event or beta radiation? Well, it's an electron. And what does the symbol for an electron look like? It is an E with a -1 here. It's got that -1 charge and an atomic mass of 0. Very, very small. So I'll go ahead and write that here. My other product has to be the result of the phosphorus atom losing that electron. Okay? And if you'll remember, my overall atomic formula for beta decay is this. So my resultant atom has to have this formula. So that means the A stays the same. 32 is going to stay 32. And the Z is going to go up by 1. Z plus 1, so it'll be 16. Okay, and again, the reason it does this is to balance out. 15 on the bottom here on the left has to be equal to -1 plus 16, and that's just 16 minus 1, which is 15. If we go to the periodic table, find the element with an atomic number of 16, you get sulfur, which is S. So this is what the correct answer for beta decay is going to look like. Last, an atom of carbon-13 or C13 undergoes a gamma decay event. Predict the products. Pause the video. Welcome back. We are going to have gamma radiation as our product, guaranteed. And what does that look like? Gamma symbol with a 0 on top, 0 on bottom. It's got no mass, no atomic mass. It's got no atomic number because there's no protons. It's just energy. So starting off, I've got carbon with an atomic mass of 13, atomic number of 6. It's going to decay, but its atomic mass is not going to change. Its atomic number is not going to change. And I'll also have, at the end of the day, a gamma particle. We're going to make the Hulk. 0, 0. That's horrible. My handwriting is so good. 0, 0. And that's gamma decay. All right, last thing that I want to talk about is the amount of energy or the capability of this radiation to do harm. So we know radiation's bad for us, but why is that? Well, what radiation does, especially in life, and you and me, is it is able to get inside your cells into the DNA. And for those of you who know what DNA is finicky and it can be altered. And if it's altered, that could end badly for you. It's called a mutation. Some mutations don't do a whole lot. Other mutations can be very harmful. So if our DNA gets messed up, there's a chance that we could get messed up. So going back to alpha decay. So the particle that is going to be doing the harm in an alpha decay is this helium nucleus. It's high energy and it's going to be flying around and it's going to try to hit your DNA. But alpha decay is relatively low energy. What is wrong with my pen today? It's not the pen, it's me. So I'll say it's relatively low energy. Which means if I expose just one of my cells to alpha decay, it could probably go in and do harm. But if I put something in front of my cells, even like a sheet of paper, something small, then it will actually block this helium nucleus from coming in because its energy is not high enough to go through that piece of paper and it won't get to my cell. So nuclear decay of an alpha particle or of this helium nucleus, relatively low energy. Moving up, the next highest is going to be the beta decay. So beta decay we'll call medium energy. So if I expose one of my cells to a high energy electron as a result of this beta decay, it'll go through that piece of paper if I try to block it, but it'll actually get blocked by your skin. So if you have like a thick sweatshirt on, a thick sweatshirt will block this beta particle and it won't be able to get through to get to your cells. And then last one, gamma particles. These are, like we mentioned, super high energy. Super high energy. These will go through pretty much everything, anything and everything that you put in front of it. And like radiation bunkers, there's like 10-foot thick walls of lead because that's the only thing that can really stop gamma radiation. Anything else, it'll go right through, go through your cells, mess up your DNA. You'll have a bad time. You probably won't become the Hulk, so don't try it.